The microprocessor has been made possible by integrated circuit technology, which can now cram hundreds of thousands of electronic components onto ever smaller pieces of silicon. Now, the microprocessor is an immensely complex piece of electronic design, but behind that complexity is a very simple principle. The basic building blocks required to make any modern computer are always the same, and those building blocks are no more than simple decision makers or electronic gates. This AND gate, for example, has just two inputs here and here and one output. Now, each of these inputs and outputs can be in one of two states. Either the lights are on or off. The state of the output here depends on both of these inputs being high, in other words, the lights being on. So this will be on only if that and that are on. In other words, it's an AND gate. One alone is not enough, both together will light the output. When simple gates like this are connected together in very large numbers, you can start to build up the very complex functions you expect from, say, a modern microprocessor. Now, a microprocessor is small, it's very cheap, reliable, and it's fast. But for an increasing number of applications, it's proving to be just not fast enough. Artificial intelligence work, Star Wars research, visual recognition systems are all making demands which the modern microprocessor and the modern computer will find it impossible to meet. Now, the problem is a fundamental one, and it's because all computers are built from electronics.
It's not possible in electronics to communicate information from one switch to another infinitely quickly. The reason for this is that they are circuits, and the speed of transfer of information in these circuits doesn't get smaller as the circuits get smaller. So that even if you make extremely fast transistors, you may be unable to transfer the information to the next one as quickly as they can switch.
So, as far as speed goes, electronics is a dead end.
In the end, electronics will reach a limit. It'll reach a communications brick wall, in fact.
So, what's the answer?
Well, the solution, we think, may lie in optics.
So here at Heriot-Watt University, near Edinburgh, they've been working on what some people rather inaccurately call the world's first optical computer. Using a large industrial laser and a maze of lenses, prisms, filters and holograms, Desmond Smith and his team have reached an early landmark in what promises to be an important new technology.
We have to reinvent the triode valve from 1907. Essentially what the triode valve did was provide a means by which electricity could control electricity and thus provide a very fast switch with no moving parts. And that, of course, is the basis of electronics, later transferred to solid-state electronics in transistors and then integrated circuits. So we've had to essentially create an optical transistor. That's to say, a small device in which a quite weak light beam, albeit these days from a laser, can actually control another light beam and give exactly the same effect that the triode valve gave. That is, an all-optical switch plus the other attribute of the triode, which is gain.
Well, the switch in this case is this tiny optical filter, but it's one with very unusual properties. We're firing a laser beam down here through the filter, and I can control the intensity of the beam just here. Now, as I increase the intensity, you'll notice there's very little increase in the output here, until, that is, I reach a critical stage when suddenly, there you are, it leaps high. Well, that's our high output, our high state, and you'll notice that the system acts as if it's got a memory, because as I pull back the intensity, it stays high until I reach another critical point and down it goes. Well, that's with me controlling the beam, but I can use light to control it. We've got a second laser coming in just here, and just flicking that in as a trigger switch will switch the output high. There it goes. Now that is very much the way a transistor works, except that with a transistor you've got electricity controlling electricity. Here you've got light controlling light.
I haven't yet explained why we think that light can actually, in the end, produce some advantages over electronics. And the reason for this is that we can use the parallelism which is natural in optics. A lens, which we've got in our eyes, and when we look at each other, can resolve at least 1 million spots. If one has small devices in which light can control light, then this lens can effectively constitute 1 million wires. And that wiring possibility, in parallel, is what gives us new possibilities for computer architecture. And if we are able to do optical switches only at the same speed as electronic switches, but multiply them by a very large amount of parallelism, might be 10,000 or 1,000,000 times, then the overall speed of processing information could indeed be very high.
Try crossing two tracks on a printed circuit board and you've got a short circuit. But you can safely cross two or more beams of light and they won't interfere with each other. Now the upshot of this is you can split a single beam into many thousands of separate parts, doesn't matter if they cross, and each of them can be processed separately. Here, a hologram splits a single beam into 25 parallel beams, and each is being controlled independently. Which may not look impressive, but it is a form of parallel processing, and that's what the research here is all about.
But with the massive parallelism that's possible, the overall data processing rate could be very high. And now you can see how it might work, simply by comparing what might happen in an optical computing device with pattern recognition or image recognition using the eyes, where we've got a device that only works in about 10 milliseconds in the neural networks, but the eye is communicating at least 10,000 channels. And so even with that slow process, working with the computer that's the neural networks, we're able to recognize each other vastly more quickly than an electronic computer could possibly do. In fact, it couldn't even do the job at all.
So far, the most complicated circuit they've achieved is this: 3 separate switches that operate one after another.
We've been able to make, therefore, the first optical circuits. One device will drive another, and then a third, and then back again to the first. That is essentially a very, very primitive computational loop. Running it round the loop, we've been able to show that, in fact, optical logic can go round without error. And that's extremely important because it was that step in electronics, when we went to digital electronics, round about the beginning of the 70s, that led, of course, to the accuracy that existing familiar computers have today. And we had to prove that that same step could be made in optics.
Well, it's taken 80 years to develop electronic computers. Will it take another 80 to develop optical ones?
Well, I don't think it'll take 80 years. I think we shall see some devices within 10 years, but I don't think we shall see a general purpose computer within 10 years. Rather, we shall see something for some special purposes. For example, if you want to do pattern recognition, what you would like to do is to access a series of memories, not one part at a time, as conventional computing does, but in parallel, so that you could actually compare a whole series of patterns to the one you're trying to recognize very quickly. It is that sort of thing that we may see a specialized device somewhere in the middle of an electronic device within the next 10 years.
Professor Desmond Smith. Well, that's it for this week's programme. We're not on the air next Friday, but we will be back in 2 weeks' time with a disturbing story about computer security which could affect everybody. But until then, good night.